Okay, good day. So let's have our discussion for welded connections. Okay, we have structural welding. So structural welding is a process whereby the parts to be connected area heated and fused with a molten filler metal. Upon cooling, the structural steel, that is, let's say the parent metal, and a weld or a filler metal will act as one continuous part. Okay, the filler metal is deposited from a special electrode. So there are several welding processes. I use either field welds or shop welds. So we have the common types of welds. So we have letter A, so fillet welds. So welds are placed in a corner formed by two parts in contact. Then for letter B, we have the groove welds. So welds deposited in a gap between two parts. Then we have letter C, plug welds. So circular or slotted hole that is filled with weld metal. It is sometimes used when more welds is needed than what is available. Okay, so that is for the common types of welds. So we have the basic processes in welding. Okay, number one, so this is, I think, the most popular one, the shielded metal arc welding. So it is widely used for field welding. Supposedly this is for welding. So it is widely used for field welding and normally done manually. Connected parts are heated and part of the filler metal is deposited into the molten base metal. As the weld cools, impurities rise to the surface and form a coating called the slug. So slug should be removed before the next pass or the weld is painted. So we have number 2, we have the submerged arc welding. Number 3, this is the gas metal welding. Number 4, we have flux cord arc welding. And number 5, we have the electrogas welding. Okay, so here are the example of fillet welds. So we have 3. So we have letter A. So we have longitudinal fillet weld. So if the length of our fillet weld is parallel to the direction of the applied force. Then we have letter B. This is for the transverse fillet weld. So this is also the length of the fillet weld. So the length of the fillet weld is perpendicular to the direction of the applied force. And we have letter C is the combination of the first two types, so the transverse and longitudinal fillet welds. Then when it comes to the design of fillet welds, so this is for the design of fillet welds. So for the computation of the nominal strength and the design strength. So for LRFDN, ASD, so we have the factors, so reduction factor and factor of safety for both LRFDN, ASD. So when it comes to the first type of fillet welds, this is the longitudinal fillet welds. Okay, for the computation of its nominal strength for the base metal, I will be using this equation. Okay, when it comes to the nominal strength of the weld metal, we'll be using this equation. And here are the definition of terms. Then secondly, we have the combination of the two types of fillet welds. That is the combination of the longitudinal and transverse. Okay, then we'll be using these two equations. Okay, when it comes to the lengths, the length of the fillet welds, so minimum length of a fillet weld may be not less than 4 times. So again, a minimum length of the fillet welds may not be less than 4 times the nominal size of the weld. Okay, the maximum size of a fillet weld along the edges of material less than 1/4 inch or 6 millimeters thick equals the material thickness. Okay? For thicker material, it may be not larger than the material thickness, less 1/16 of an inch, or in millimeters, this is 1.6 mm. Okay, so here are the types of welds or fillet welds. So we have letter A. This is the with a convex surface. With I think this is we call them the leg or the legs. So in some references, so the legs can be used as A, or can be denoted as W. So we have, for example, we have equal legs. Okay, that is for the convex surface. Then letter B is the concave surface. Then letter C is we have the unequal for unequal leg fillet weld. So for A and B we have equal legs. Unlike C. So we have this is the weld base. This curved surface. Then we have the theoretical or diagrammatic face of the theoretical throat. So this is assumed to be, or I think this is supposedly 45 degrees. So if we are to compute for its resistance or nominal strength, we'll be using the cosine of 45. So I think cosine of 45 degrees, we have that as the cosine of 45 degrees is 0.707 of this leg dimension of the side side A. So 0.707. Okay, the next. Okay, so we have table 14.1. So we have the load type. Okay, for the load type and direction relative to weld axis. So we'll be using this table later on our example. Okay, when it comes to the computation of the nominal strength of a fillet weld, so F sub NBM or the F sub NW for both KSI or megapascals. Okay, so for the base metal, so governed by the table, I think this is for another reference, J sub 4. Then for the weld, when it comes to shear, so we'll be using a reduction factor of 0.75 and 2.0. And we have 0.60 of F sub E XX. So the filler metal electrodes for the shielded arc welding are listed as we have E60XX, E70XX, etc. Okay, in this classification, the letter E represents an electrode. While the first set of digits, so we have that, for this example, we have the 60, 70, we have 60, 70, 80, 90, 100, or 110, indicates the minimum tensile strength of the weld in KSI. So which means if we have this E60XX, so its minimum tensile strength is 60 kips per square inch. So just an example. Okay, so let us continue our discussion. So we have the remaining digits may be used to specify the type of coating. So because the strength is the most important factor to the structural design, we usually specify electrodes as you have E70XX, E80XX, or simply E70, E80, and so on. So for the usual situation, we are using E70 electrodes for steels with Fy, with values of Fy 36 to 60 KSI, while we have E80 for steel with Fy equal to 65 kips per square inch. So to summarize that part, so again, we usually, if we have, for the case, so we are using E70 for steels with Fy equal to 36 KSI 2 60 kips per square inch. And we are using E80 for steel with Fy is equal to 65 KSI. So in addition, so let us continue our reading. So in addition to the nominal stress given in table 14.1, there are several other provisions applying to welding given in section of the LRFD specification. So among the more important are the following. So you have number 1, the minimum length of a fillet weld may not be less than 4 times the nominal leg size of the weld. So I think that is also specified earlier from our table, from this table. Then we have, I think the same with number 2, the maximum size of a fillet weld along edges of the material less than 1/4 inch thick. So it is the same as the this one, the second sentence. So the 1/4 inch or the 6 millimeters. Then we have number 3. So the minimum permissible size of fillet welds as of the AISC specifications are given in table 14.2. So this one. Okay, so they vary from 1/8 of an inch for 1/4 inch or thinner material up to 5/16 inch for a material over 3/4 inch in thickness. So the smallest practical weld size is about 1/8 of an inch. And the most economical size is probably about 1/4 or 5/16 of an inch. So the 5/16 inch weld is about the largest size that can be made in one. So this is our reference so when it comes to the minimum size of fillet welds. Okay, so this is for the introduction of a welded connection. So I think we can now have our first example. Okay, for our example, I determine the design strength and the allowable strength of the tension member shown. So we are to use E70XX E70XX electrode. So this is our connection. So we have a plate which is that is 10 millimeters thick, 100 by 100 mm. Then, so we have a plate, or this is the gusset plate, 15 millimeters thick by 200 millimeters. Then, the given length of the fillet weld, the length of the fillet weld is equal to 125 millimeters on two sides. So this portion of the connection is also known as the end returns. So end returns, or in some references, we call it a boxing. So just the boxing at the end of the fillet welds. So the purpose of end returns or boxing is just to provide. Okay, so end returns or boxing provides. It provides better fatigue resistance. Okay, so that is the purpose of the end returns or boxing. So it provides a better fatigue resistance for the connection. Okay, so let's have, okay, on the fillet welds. So let us determine what will be the dimension of the leg. So let's say this is the leg A and A. So how do we determine the value of the required leg of the fillet weld? So for our A minimum, this is the minimum dimension of the leg of the fillet weld. So we'll be basing on table 14.2. So, but before that, what are the thickness of our plates? So the thickness of our plates, the gusset plate is 15 mm, and our tension member is 10 millimeters. So therefore, we are to consider the thickness of the smaller plate or the thinner plate. So we are to adapt, or we are to consider the thinner plate, that is the 10 mm. So if the thickness of our plate is 10 millimeters, so we proceed to table 14.2. So material thickness of the thinner part. So material thickness of the thinner part joined in mm. So we have, that is the 1/4. So we have 1/4 inch or 6 millimeters to 13 mm. So 10 millimeters is somewhere between 16 and 13. So the minimum size of the fillet weld is equal to 5 mm. Okay. So our minimum leg dimension for the fillet weld is equal to 5 millimeters. So what about for the maximum? Okay, for the maximum dimension of the leg of the fillet weld, we'll be basing on this table. So the maximum size of a fillet weld along the edges of the material less than 1/4 inch, 6 mm. Okay, for thicker material, it may not be larger than the material thickness less 1/16 of an inch, or that is 1.6 millimeters. So since for this example, the thickness of our plate is greater than 6 mm. So for the maximum possible dimension of the leg, this is our A max. So the thickness of our plate is 10 millimeters. So we are to subtract 1.6 mm, and this is equal to 8.4 millimeters. So the possible value of the leg of the fillet weld is from, so we can choose somewhere between 5 millimeters. That is from 5 mm to 8.4 millimeters. Okay, so we are to use any value from 5 millimeters to 8.4 mm. That will be acceptable. But for this example, just for this example, I'll be using use A is equal to 6 millimeters. Okay, that will be the leg of the fillet weld. So when it comes to the computation of the minimum length, let us check. This is for the minimum length of the weld. So for the minimum, let's say minimum L sub W is equal to 4 times the value of the leg of the fillet weld. So this is equal to 4 times 6 mm, and this is equal to 24 millimeters. But on our actual connection, so the actual length is equal to 125 mm. So therefore, it is okay, since this is just the minimum, a minimum value of 24 millimeters. So this is less than the actual length of the fillet weld, which is equal to 125 mm. Then we need to check, for this example, we need to check the ratio of the length of the fillet weld to the dimension of the leg of the fillet weld. That is the L sub W divided by A. So this is equal to 125 millimeters divided by 6, and this is equal to 125 divided by 6 is equal to, let's say this is 20.83. So the limitation when it comes to the ratio of the length of the fillet weld to the length of the leg of the weld, so L sub W over A should be less than 100. So we satisfy that condition. So for this case, the value of beta should be equal to 1.0. So for the cases that, for example, the length of the weld over A is greater than 100, so we'll be using a multiplier, or we are to compute the value of the multiplier beta, which is equal to 1.2 minus 0.002 multiplied by the L sub W divided by A. But the limitation of this multiplier should be less than or equal to 1.0. So maybe we can discuss this multiplier, this factor, on other example. But for this case, it is simply equal to 1. Okay, so and then for example, we are required to compute for the length of the end returns or the boxing. So we can compute for the length of end returns just to improve the fatigue resistance of this connection. That can be equal to twice the value of A. So the length of end returns or boxing can be twice of the value of A. We are using 6. So we can use 12 mm. So that will be the length of the end returns or the boxing. Okay, so let us now compute for the design strength of the weld. Okay, for the design strength of the weld, so this is a longitudinal fillet weld. So from our reference, so we'll be using this formula. So when it comes to the strength of the weld metal, we'll be using this equation. So R sub n is equal to F sub n W, A sub W E. So for the design strength of the weld, this is we have R sub n is equal to F sub n W multiplied by A sub W times A sub W times E. So when it comes to the value of the F sub n W, so F sub n W is equal to so from our reference again. Okay, from this table, for the nominal strength, for the weld, that is 0.60 of F sub E XX. So this is equal to 0.60 of F sub E XX. So that is for the strength of the electrode. So the strength of the electrode is 70. Again, so from our it was stated a while ago that this corresponds to the tensile strength of the electrode to be 70. This is 70 KSI. So 70 KSI, this is approximately equal to 482 megapascals. Okay, when it comes to the area of the weld, A sub EW, so A sub EW, so again, this is the throat of the fillet weld. So this is 45 degrees. So our A sub E, our A sub WE is equal to 45 degrees A multiplied by 0.707. Then we are to multiply that to the length of the weld. So this is multiplied by the L sub W. So take note that we have two lines of weld. So we are to multiply this one by 2. Okay, so we are now ready to substitute. So for the design strength, this is for the nominal strength of the weld. R sub n is equal to F sub nw is equal to 0.60 of 70 ksi, or approximately equal to 482 megapascals. This is newtons per square mm. Then multiplied by A sub WE, that is the leg. So again, we are using the leg of the fillet weld as 6 mm. Then multiplied by 0.707, that is cosine of 45 degrees. Okay, so this is multiplied by the length of, or the leg of the fillet weld is equal to 6 mm multiplied by 0.707, to be multiplied by the length of the weld, that is equal to 125 millimeters. So this is multiplied by 125 mm. And take note, we have two lines of weld, so we are multiplying 2. So if we are to do unit analysis, obviously the remaining unit for this one, this is already in square millimeters, so cancelling square mm, that will be in newtons. So dividing the entire value by 1,000 newtons. So this will be the nominal strength of the weld. So computing for the value, this is 0.6 of 482 megapascals. Then 6 multiplied by 0.707. The length of the weld is 125. We have 2, so multiplied by 2. Then this is to be divided by 1,000 to be in kilonewtons. Okay, so let's say this is 306.70 kilonewtons. Then for the two methods, this is for the LRFD, we have a reduction factor of 0.75. So we have the design strength. This is P of R sub n is equal to 0.75 multiplied by 306.70. So the design strength will be equal to, multiplied by 0.75, that is 230. So this will be 230.02. So a design strength of 230.02 kilonewtons. So when it comes to the ASD method, we have a factor of safety equal to 2.00. So for the allowable strength, this is the R sub n divided by omega. So our R sub n is equal to 306.70 kilonewtons to be divided by 2. And the allowable strength is now equal to that is 306.6966, or that is 306.7 divided by 2. Allowable strength is equal to 153.35 kilonewtons. So this is 153.35 kilonewtons. So this will be our answer. Okay. So for the design strength and the allowable strength of the weld, based on the given strength of the electrode. This will be our solution for this example.